Human approval is only half the problem. I'll show how LangGraph checkpointing lets agent runs pause cleanly, survive crashes, and resume from the exact state that matters. This is the setup you'll be able to run after this, which pauses for approval, saves state, and resumes to finish without replaying steps. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Checkpointing matters when agents take many steps, call external systems, or wait for human approvals. The pain is repeating expensive work after a crash or a decision loop. Success looks like a paused run that picks up exactly where it left off, with no double sends and no wasted recomputation. LangGraph gives that at the workflow level, rather than forcing you to sprinkle persistence calls through every function. The high-level idea is simple. We run a tiny directed graph of nodes. Each node can save its local state to a checkpointer after it runs. Later, we can resume from the saved snapshot. That snapshot can be inspected, updated, or branched. Strengths are clarity and reproducibility. Weaknesses are that you need to think about which pieces of state are safe to persist. We will build a small demo that writes a draft, pauses for approval, and then resumes to either send or keep the draft. The demo uses a memory-backed checkpointer, so you can see saved snapshots and fast branching before we try persistent storage. Now, we will compile and run a minimal graph that writes a counter to state. This snippet compiles a tiny LangGraph that saves state with the built-in MemorySaver checkpointer. The function step increments a counter named n inside the state, so we can see persistence happen. A StateGraph is created with a single node named step, and start and end edges wire it into a runnable flow. The graph is compiled with MemorySaver, so every node run writes a checkpoint. We then invoke the graph once with a thread configuration to scope checkpoints to a thread. Finally, graph getState reads the stored state for that thread and prints the counter. The printed saved n confirms a checkpointed write occurred and can be retrieved. Next, we will create a draft and pause the run so human approval can happen later. This example creates a single node LangGraph that generates a draft, then waits for approval, using the same MemorySaver checkpointer. The function agent writes a draft entry when none exists, and on later runs either marks the run sent or sets a wait status depending on the OK flag. A StateGraph is built with one agent node and compiled again with the existing checkpointer, so state persists across runs. We invoke the graph for thread T2 with a rec string to create the initial draft. Then, graph.getState pulls the current state for inspection. The printed paused and has draft values verify the run stopped for approval, with the draft already saved. Now, we will flip the approval flag and resume the paused flow to complete the action. This code resumes the paused run by flipping approval on the saved LangGraph state. The call graph.updateState writes OK equals true into the same thread's checkpoint without replaying earlier logic in the application code. Next, graph.invoke continues execution from the compiled graph using the persisted context. The agent node now sees prior draft content and the new OK flag, so it returns a sent marker. We fetch the latest state with graph.getState to verify the outcome. The printed, delivered, and kept draft values confirm the agent completed the action and reused the existing draft rather than regenerating it. Next, we will inspect the history of saved snapshots to see the checkpoint timeline. This snippet inspects the run timeline using LangGraph's graph.getStateHistory. The variable hist collects all saved snapshots for the thread, which is useful for incident-style debugging and auditing decisions. We then read the latest state with graph.getState to check the final condition. Counting hist entries shows how many node-level checkpoints were recorded across pause and resume cycles, which helps confirm no unexpected replays occurred. The final sent flag reflects the terminal outcome in the same thread. The printed values demonstrate both the number of persisted steps and that the resumed run actually finished successfully. Now we will branch from an earlier snapshot to try an alternate approval outcome without touching the original run. This example branches from an earlier checkpoint to test a safe alternative without touching the main run. Using LangGraph's graph.getState history, we pick the first snapshot and seed a new thread configuration, CFGB, via graph.updateState. We then set OK equals true on the branch to simulate an approval outcome and invoke the graph to complete the flow. Finally, graph.getState reads the branch's terminal state. The printed branch delivered and reused draft values show the new thread finished successfully while reusing the prior draft, enabling quick recovery or what-if retrons without replaying the original workflow. This toy example maps directly to real projects that need durable, human-in-the-loop orchestration. In a product setting, you would swap MemorySaver for a durable saver that persists to disk or a database and run many concurrent threads. The core idea stays the same. Checkpoints represent meaningful milestones you can audit, update, or branch from. Recap. What it is: a workflow-level checkpoint and resume system for LangGraph that saves node state and thread context. When to use it: when runs are long, involve humans, or call fragile external systems, and you want to avoid replay. One caveat: you must model which state you persist carefully to avoid stale secrets or large blobs. Next step: try tuning how often you checkpoint and add timing and success counters so you know the cost of each persisted step and can choose a checkpoint frequency that balances speed and recoverability. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.